Hey HMS modelers, this is Mike Bartles from the Hydrologic Engineering Center. In this video, I'm going to talk about how to select an appropriate routing method because there are quite a few to choose from and each have their own advantages and disadvantages. A good bit of material within this lecture was originally developed by Gary Brunner, also from HEC. This lecture is designed to help modelers identify which hydrologic or hydraulic routing method is most appropriate for a given problem. We'll go over considerations and study objectives, and I'll also present some rules of thumb that have been helpful to me in my career. Before we start, keep in mind that all routing methods are a simplification of the real world. Therefore, you must identify the aspects of the physical system that will most affect reach routing and go with the model that best addresses those needs. For instance, if there is going to be a significant amount of structures that affect the water surface profile in your study area, you must use a routing method that captures the influence of backwater. Furthermore, the appropriate routing method provides the necessary information to meet study objectives. If the goal of the study is, for instance, to identify the peak flow at some point in the watershed for sizing a culvert, a hydrologic method may be an appropriate choice. Here are some questions to ask yourself when starting a study. For each of the 8 available routing methods within HMS, how does each method represent open channel flow processes? What are the method's advantages and disadvantages? What input data is required by the method? And can the method supply the required output information? Some additional factors to consider include: what type of study is being undertaken? What's going to be considered? Will one or more reservoirs be simulated? Will modifications to one or more channels be simulated? How much detail is required by the study? Is the study quick and dirty? Or is a high degree of accuracy required? What are the characteristics of the physical system in question? And we'll come back to that topic over the next few slides. What routing methods are you most familiar with? And how much time and money is available for the study? Now let's talk about several physical considerations. Backwater effects refer to an increase in the upstream water surface elevation resulting from things like tides, bridges, hydraulic structures, and other obstructions. In general, hydrologic methods do not simulate backwater effects, with the exception of modified poles, which can if the storage outflow relationships that are used were derived from a hydraulic model that did include backwater effects. Conversely, hydraulic methods can usually simulate backwater effects. Notably, the kinematic wave method cannot simulate backwater effects due to the underlying simplifications of the momentum equation within that method. Floodplain storage can also have a significant impact on a routed hydrograph if the amount of storage they provide is large compared to the hydrograph in question. If there's little to no storage within the floodplain, the inflow hydrograph will likely experience little to no translation or attenuation as it moves through the reach. Important factors to consider include the width, the slope, and the roughness of the floodplain in your specific application. If floodplains are important to include, you must use a method that can separately compute the effects of the overbank areas from the main channel. For example, the Muskingum-Kunj method, when using an 8-point cross-section sheet, can do just that. However, the Muskingum method cannot. If the floodplain is incredibly wide and flat, and flow actually moves perpendicular to the main channel, 2D modeling may be required to accurately simulate the movement of water. In those cases, the 2D diffusion wave method can be used. Confluences can be sources of backwater effects, like those that were previously mentioned. In the image to the right, the Yellowstone River and Missouri River confluence is shown. If, say, the Yellowstone River is flooding, significant backwater effects can be experienced for miles on the Missouri River. If there are significant effects from a tributary, you should use a method that can account for backwater effects. However, if backwater effects from the confluence are negligible, all hydrologic routing methods are fine for use. When there are flow splits and reversals, like those afforded by tidal bores from tropical storms, the full dynamic wave equations should be applied, which are available for use within HEC-RAS. Regarding sub and supercritical flow, hydrologic methods don't know the difference between the two. If the flow regime changes for long stretches within your modeling domain, or if stage is an important factor, the reaches where a different flow regime is present should be broken out and isolated. In general, intermittent supercritical flow can be ignored for hydrologic routing purposes. When observed data isn't available, physically based methods should be used for 2 reasons. 1, it's easier to estimate the input data, and 2, the results will be more reliable. However, when observed data is available, your model must be calibrated and validated. Make sure you use multiple statistical metrics to ascertain model performance. Now let's talk about slope, because that's an incredibly important factor to consider when choosing a routing method. In general, as the slope gets flatter, hydrologic methods begin to fail. And this is due to their derivation. All hydrologic methods either get rid of the momentum equation entirely or make massive simplifications. When slopes get flatter, the acceleration terms within the momentum equation begin to become more and more important. In the example image shown here, above river mile 75 or so, the slope is relatively steep, and most hydrologic routing methods will do just fine. However, below river mile 75, the slope dramatically flattens. Very few hydrologic routing methods, if any, will be accurate downstream of that point. And here are some rules of thumb that you can use. For channels with bed slopes greater than 10 feet per mile, most hydrologic routing methods are okay to use. For channels with bed slopes less than 2 feet per mile, most hydrologic routing methods are going to fail and produce erroneous results. In between 10 and 2 feet per mile is kind of a gray area. The accuracy of the results depend upon the channel properties, the chosen method, and the rate of rise of the hydrograph. And Ponce published a study in 1978 that took a look at the use of the kinematic wave and diffusion wave approximations when routing various hydrographs over varying bed slopes. And he found that the kinematic wave routine produced reasonable results when the following inequality was satisfied. If the kinematic wave approximation works, most hydrologic routing methods will do just fine. He also found that when using the diffusion wave routine, reasonable results were produced when the following inequality was satisfied. Now, these two criteria, when used together, can be used as bookends of sorts to predict whether certain routing routines will produce reasonable results or not. Now I'll present some tables that summarize the factors we just discussed. Now, these aren't hard and fast rules or anything like that. These tables are meant to provide a quick way to identify reasonable modeling choices. When no observed data is available, it's difficult, if not impossible, to have faith in the estimated parameters for, say, the lag and Muskingum methods, so it's best to not use them in those situations. Conversely, methods that can estimate parameters using physically measurable data are a good bet. When backwater effects are present that will influence the routed hydrograph, only the diffusion wave and modified poles methods can produce accurate results. Other hydrologic methods won't work well. When floods produce stages that go out of bank and there's significant storage that will affect the results, only methods that calculate hydraulic properties of the overbanks separately from the main channel are appropriate for use, like Muskingum Kunsch. Here are some slope and hydrograph considerations. In general, if channel slopes are over 10 feet per mile and the hydrograph is relatively slow to rise, using the Ponce criterion, most routing methods will do just fine. But as channel slopes decrease, and if the rate of rise of the hydrograph becomes appreciably fast, hydrologic routing methods start to produce erroneous results. For channel slopes less than 2 feet per mile, only the full dynamic wave equations will do a good job producing results. Now in review, the most appropriate routing method for a specific situation depends upon many considerations like study constraints, data availability, output requirements, and physical considerations. Important physical components of the system in question include backwater effects, floodplains, and channel slope. Feel free to use the rules of thumb and tables presented near the end of this video to quickly identify appropriate methods. Thanks for watching this video, and I'll catch you in the next one.